with Guglielmo Lami, Guglielmo pertaining gestione in FIFA, and it's currently full block in 3G. And we're working on a various topics, including Magic, on Q3, and other several topics in medical physics and science. So, sure.
Okay, thanks, Gabriele. Thanks for the invitation to be here. So, the fact I want to talk in parallelism. So, my talk will be about both quantum information and quantum many body systems. So, the intersection with these terms now, in particular, in the context of non-Gaussianity and how we can drive the emergence of some of universal dynamics in many systems. So please feel free to interrupt me if you want, better question. To clarify what to say, so this is a joint work with many people. Most of them around people, yes, but not only. Here in this slide, there are several people of Indian origin. I let you get to the result of this one of Palermo. And the content of the paper is the content of the book is the full paper. So I will briefly introduce the big framework, quantum information framework, that basically big umbrella under this work is having something that is quantum resources, and in particular, I will focus on non-familiarity and non-science. This, and then I will introduce our model. This is a model Matchgate, developed with some non-Gaussian gates. And then we will move to results. So I will start with this big idea of quantum resources. Maybe some of you are familiar, more familiar than me, maybe others no, but the idea is quite simple. So it's a big general framework that has been constructed in quantum information, which relies on some simple ingredients, let's say. So there are several ingredients. The first one is defining what is the set of free states, schematically. And so these states free are states to not carry any resource. For instance, you might be familiar with entanglement, and entanglement is the resource theory. And here the free states, the states that carry no entanglement, are the several states. But this concept is more general, in fact. So quantum resources can be applied much more generally than only entanglement. Second ingredient is what is a free operation. So somehow a free operation is something that is easy to perform, in a laboratory. Again, with the example of entanglement, computation are local operations. So something you can here, like Alice can do is part of the state without into entanglement of preparation, but again, framework much more general than entanglement. The third ingredient is then having a resource model that is somehow a measure of this idea of this fund. For instance, for entanglement, might be familiar with entanglement or entanglement negativity. Each of these are proper resource models. So in general, people often draw something like this. So we have states, some of them are free, and free operations have free state, but of course the space of space is much larger, and states that belong here have some resource which can be exploited, as for instance, entanglement. So in entanglement, here we for instance have bad period. Okay. So there are many ways of using this general framework to describe different kind of feature of quantum state. So like the most times one is entanglement, the reserves, free states at the set of those states, and free operational local operations, communication. But this same mathematical framework can be applied to other concepts like non-Gaussianity, and here the states that are here somehow are the Gaussian states, and the free operations are the Gaussian. And there are many others. One that is quite known is essentially non-stabilizer. Stabilizer states are the free states, and Clifford operation are the free operations. So I will briefly describe this one because it's partially related to my work. But the rest of the talk will be about non-Gaussianity. So to describe those theories, stabilizers, one will need some dictionary, and here the dictionary is simple. So first, let's say we have to define what is the Pauli group. Pauli group is essentially here n qubits is the set of Pauli operators to the n qubits. And importantly, there are some unitaries that map Pauli into Pauli in some cases. And these are known as Clifford unitaries, Clifford operations. And stabilized state, just to find out the state, you can get out of some reference state just by using a Clifford transformation. And important, stabilized described by a simple representation because basically they are stabilized, so they are plus or minus one eigenvectors of some Pauli operations, and this is defined their stabilizer group. So in this framework, basically again, the result is non-stabilized. So how much a state deviates from being a simple stabilizer, let's say, the state that carries the result of the state, and the operations that are cheap, that are free, are simple. So operations that map a Pauli into a Pauli. State is that I will mostly be focused will mostly be focused on non-Gaussian instead. So again, we need a dictionary, which is a bit different but somehow similar. So you might be familiar with the Jordan-Wigner transformation. So basically, when you have n qubits, you can have some mapping between the Pauli operators of these n qubits and some Majorana operators of the fermionic nature. The mapping is like this. The mapping is like this, basically, and these Majorana operators are usual Majorana operators, so they are anti-commute. And again, here there are some easy to perform transformations and are Gaussian transformations that basically map a Majorana into a simple combination of Majorana. And how to perform to treat and describe this state is through a covariance matrix, basically a matrix of two-point correlated functions that completely describe the state. The fact that Gaussian states are just states, and state from a level state when applying use some Gaussian principle. So again, you might see the similarity between this slide and one about stabilizer. It's very similar. And again, it's described by a result. All right. So Matchgate are another name for Gaussian transformation, basically. Gaussian operations are like the way many body scientists put this, but computer scientists introduced as far as this idea of matchgates that turn out to be the same. So they are double named. So matchgates are simple Gaussian transformations. So if you have only two qubits, you can find out that they have this particular structure. It's a two qubit matchgate, and there's a particular structure with one. And again, both Clifford and Matchgate are stimulable, classically stimulable. Why? Because with Clifford, one can evolve the power generator that describe the complete detail, and then you can evolve them in a classical computer. Some known classical algorithm. This was found out by Gottesman and others. And for Matchgate, is exactly the same, just that instead of reporting power generators, we have reported the covariance method. Many years. Because basically covariance method is like all 2n by 2n and by n. And you have to conjugate it by a matrix with two matrices that are rotated. So that's for even more than make it collected by the yeah. But for the times batch. Okay, so both Clifford and Matchgate are classically stimulable. But of course, they are not universal to quantum computation. Otherwise, everything will just reduce to performing some classical simulation. But we know that quantum computation does something to the story. So this is especially the fine dimensional counterpart which trying to use to UniPa. Yes, this is for fermionic distance embedded into qubit. But yes, the same. We also use Matchgate that like linear or quadratic. Yeah, that's and we also can use the differentiate out by quadratic. Like that's yes, exactly. If you want, yes. Each of these gates is basically the unitary roots is quadratic. Java with fermionic, but yes, very similar to the one. And Java generally defined. I think it would yeah. Yes. So Matchgate and Clifford are classically stimulable, but they are not universal to quantum computation. What you have to get universal quantum computation for magic if you want. In particular, what you have to have is for Clifford, you have to have a single extra single duplicate, and it has a particular phase in 5/4. It is just adding to the Clifford set gate enable universal computation. Similarly, for Matchgate, you just need to add another single one gate. This is the swap gate. It's simply a gate that swaps. Swap plus Matchgate is enough for universal computation. Swap when it is non-Gaussian because one single Majorana in 3 Majorana. Okay, so in general, these two stuff, so non-Clifford and non-Gaussianity are often called related to magic. No, because they have different determinants. And which means that to replace them. So the general idea of this talk is that we just know that quantum results, so both non-stabilizers and non-Gaussian are required to have somehow genuine quantum complexity, genuine complex quantum dynamics. But the point is how much you need to get complex quantum dynamics. So to do this, I will focus on like some way of detecting this complexity, essentially, and it's based on entanglement. So I will first describe what is what happened in Matchgate circuit of entanglement. In fact, Matchgate circuit have some strange and anomalous entanglement features that we'll need to describe, and they are anomalous in three ways. They have anomalous entanglement growth with time. They have an anomalous page view, and they have anomalous behavior when you have the measures. So entanglement here, I think just constant simple bipartite entanglement entropy. So let's describe it. So you take a system, you evolve with some matching circuit, and you realize that the entanglement here it grows with time, and it grows as square root of this. Without this figure, this growth here. So it grows, but not fast. But instead, if you take the same system, you apply a generic circuit, for instance, a random circuit, you will find out that the entanglement grows much faster, linearly in time. So this is it's weird. So a Matchgate systems have entanglement grow but slow. So this is the first point with pattern. Notice that also Clifford circuit, while being non-universal, still their entanglement grows linearly in time. So they are particular, but still they are complex enough. Entanglement point of view.
Here, when you say to this curve, the average,
Yeah,
average over all.
if you want. But the more to take one instance only, I think we can
The variance is very small.
yeah.
Is there a general way to find
In
it?
fact, the variance is next to the
Is there a general way to define unique measure?
yes, of course. I mean, for a generic circuit, is R measure, and for match circuit, you can define a R measure, analog. Yes. So overall, the idea was that Matchgate slow entanglement group.
Avremo la necessità di utilizzare il tavolo per lavori di utilizzamento. Potrete spostarvi di nuovo a D, che questo è poi il fronte. A che ora finire? A mezz'oretta li faccio aspettare. Oh, ok.
Random non important. It depends how you find it. Generally, because even keyboard is yes, in which just yes, about clock specific was another response. There is also some behavior about the how fast is around the government. Starting in this one, this is random like two body or yeah, you want it. No, you take a global take time.
Come around few people are theory interruptions or
Yeah, using for local interaction. Yeah.
so if you work like around
If you look just around usually, I mean, you know, it's at the time because just apply one single random with the random state and then there is no entanglement group. Yeah, that some.
I mean you could do like every layer
Then it is I mean, There's no point in doing the product random. That is that thing.
And if equal, sorry.
Free, yes. For everything local, pyramid.
But at some point, it should start to be, yeah, the
So I will think about this is the average. The variance also some behavior. Like if you study the entanglement growth, the variance of the entanglement growth in generic circuit, people study this and discover that follows a celebrated law called the Kaplan-Diamond scaling, EPD, which is the following. So the variance of the standard deviation of the entanglement grows as e to the 1/3. This exponent is exactly belonging to the class of described by Parisi and others. They discover it in some growth phenomena in classical physics, but it applies to here. We generally describe every growth phenomenon. So generic theory has this growth of variance of entanglement entropy that follows KPD, but Matchgate circuit no. We have another exponent. So this is another difference. Okay, this was about the stuff. Here instead we will consider the base cube. So yes, following to take a random fermionic Gaussian state. Okay, so no time, you just take that, pick a random fermionic Gaussian state out of the space, and you compute the entanglement entropy over every possible vector system. You have n qubits and you divide I and n minus I to 1. And you do the same instead for a random state. So you keep a state, completely random state on top of the state. So if you do this for the random states, you find this cube is known as page cube. So the entanglement grows until the out of the system, then it decreases magically. But for Matchgate state, if you want Gaussian state, the cube is very different. So it's like way below the maximum given the page cube. It is another difference. So Matchgate circuit have again much less entanglement than generic state. Stabilizer state have more or less starting the same page cube as generic state. So they are much closer to generic states than Gaussian state.
Yeah, you're thinking of system by
You take I sides and n minus 5 and you compute with the baby. So this was the second difference. Finally, we split the third one. So the third one is about basically the final stage that is some dynamics. So suppose you have a circuit and you apply layer by layer, and of course, if you left enough time, if you wait enough time, then the final state in general will have this volume law. We'll have a volume law entanglement. That means that essentially the entanglement over like up chain is expanded. You have just to wait enough and you get expensive entanglement. All right, but people in many bodies got interested in what happened instead of just having unitary dynamics, you instead add measurement in the system. So suppose that after each unitary layer, you have that each qubit for some reason it got measured with some probability. So you have this kind of setup. And well, here we have two facts because the dynamics create the unitary dynamics create entanglement, but when you apply measurement, the measurement destroys entanglement. We have a competition between these factors. And what happens is that in generic circuit, there is a crystal system. So there is a probability value beyond of which entanglement is completely suppressed. We have what is called area law. because essentially measurements are too strong and too frequent that we destroy all the time. And the final entanglement is just bounded. But instead, if the measurement rate is low enough, you get again the volume loop. So it is retained for more measured unitary dynamic speed. And even if one is the bounded with it should be some adaptation. This is the same also for click here. So we have exactly the same technology. So volume low, area low, and critical point. But instead, Matchgate here is completely different. In particular, there is a small measurement rate. You are already destroying the volume. So you get a log low. Log low means that the entanglement, instead of growing linearly with the size end, just grows as log. So this is basically saying that unlike in generic circuit, makes this circuit generate some entanglement, but this entanglement is very fragile under measure. So you just add a little bit of measure to your system, and you pass from having a volume law of entanglement, of extensive entanglement, to just log entanglement. So this is another difference. Yes, of course, it's also different. It depends on like the probability in general depends on both the details. But most importantly, you have what the phase depends on and what the precise thing. The precise value of the critical point is maybe less interesting in general. Okay.
And I think the measurements are Gaussian.
Here, yes, they are like standard measurement. Yes.
Is there a generic group of these measurements to be?
I guess so. I think it can just apply a single qubit Gaussian. You tell them can define. Okay, so basically what I will describe now is we try to answer this. So how much non-Gaussianity you need to add in your dynamics to let these 3 points describe being. So recovering a linear growth of entanglement with time, recovering the conventional cage cure, and recovering a volume low under external measurement. So because we saw that Matchgate that lack non-Gaussianity have anomalous points. Now, if you have non-Gaussianity, you should recover the usual feature. But how much entirely non-Gaussianity you need to do so? This is the big question. So to answer this question, we take a particular model called Doppler Matchgate circuit. So Doppler is simply the following. So we have a circuit in which many of the gates are simply Gaussian, so they are match gates. So match gates in Gaussian is the thing. Most of the gates are Gaussian match gates, but few of them instead are non-Gaussian. For instance, you can take this wall, this store. So you are doping a simple Gaussian Q swap gate that create complexity. Then eventually you can also measure. Okay, so this adding this non-Gaussian doping there is an emergence of some universal behavior. Like when it is universal, it means these features that are present for generic states of generic dynamics. Okay, the feature I described before. Okay, so more specifically, you can take, for instance, that each unitary has some probability of being Gaussian and some probability of being non-Gaussian. So few probability of being non-Gaussian and 1 minus q of the Gaussian. Then you take this q to be small n. If you have measurement, you can with measurement you can start. Each qubit is measured with some probability. So since each unitary has probability q of being a non-Gaussian, then the total number of non-Gaussian gates you are accepting to is like basically q times n, because we have n qubits, times p, which is the total time. So this is the total number of non-Gaussian doping you're adding into the number. So what we do here, we got several numerical results, and to get these numerical results, we adopt a trick. So we take this model with Gaussian or non-Gaussian gates, but we constrain everything to be Clifford. Okay, so we have gates that are Gaussian or non-Gaussian, but both of them are Clifford. Why we do so? So you can do simulation up to big size. So as I showed you before, Clifford the state, Clifford dynamics is always Clifford, no matter if it's Gaussian or non-Gaussian. Okay, so we take everything to be Clifford so that basically we can run simulations up to big system size, like very cheap. So now, okay, here basically, I'll tell you something. So basically, these blue gates are now Clifford, but also Gaussian, while the purple one are just Clifford, non-Gaussian. And then it turns out that this Clifford Gaussian gate has an interesting structure. So if you require a gate to be both Clifford and Gaussian, then what you get is simply a permutation of Majorana. So basically, you get that is the gate when applied to the later, it just turns them. So in fact, we also use this structure to get some analytical insights, because basically the circuit is very simple from the Majorana perspective. Okay, now what is the evolution? Okay. I mean, what we are talking about. Yes, okay, I can give you write down the task gauge now, but essentially what we like are like this. Yeah, segmentation.
Like, you know,
I don't have to check. But any case, we are not using something up to phases. Okay, so now I need to results. So first, let's remove measurement. So no measurement, just simple unitary dynamics, and you have some probability on each unitary to be non-Gaussian. So what happens is the following. So we have the entanglement. Our entanglement grows with time. Okay? Basically, here take time in such a way that eta t basically this eta tn is the total number of non-Gaussian gates. Okay? So q is eta over n. So I set q equal eta to the n over n. So the total number of non-Gaussian gates is like q times n times t. So it's basically eta t. So here, what I got here is total number of Gaussian gates, eta t divided by n. Okay. So what happens is basically at the beginning, the system is not realizing that you are adding something, because you are adding a little bit of stuff. So at the beginning, it doesn't realize. And the entanglement group in the way Matchgate in the way Matchgate has the entanglement group. So it's good, but just not with time. Okay. So at the beginning, the system doesn't realize that you're doping the system with some Gaussian stuff. It's just growing entanglement, but it's growing slowly. The initial phase. Okay, but at one point you start, the system starts to feel the effect of the doping stuff, and at that time the group passed from being a square root of t to t, basically. Okay, so you have a crossover between square root of t here at the early times and t at the final time. Okay, so you start from something diffuse, this is called network physics, to something ballistic. And what is this crossover time? Well, it is line basically, and it just corresponds to when the total number of non-Gaussian gates that you added is n. So it's very simple. So you need n gate, n non-Gaussian gate, to have the initial growth becoming the usual one, but becoming itself in general. So n non-Gaussian gates are what you need to usual entanglement. Same thing for the basically the variance of the entanglement. So at the beginning, the system is not feeling that you are adding some of the fun. At the beginning, it's just Matchgate. Okay, so the entanglement grows, but grows with exponent 1.4. Okay, at late time, you start to feel that you add enough non-Gaussianity, and then it start to behave like with this case, this case. So growth as t one term. So this is the final time. So you start from this, and you here and the midwire, the between is not precise crossover, and again this crossover is not precise time. When the number of non-Gaussian gates you add, it's just okay. So again, you need n non-Gaussian gates to recover generic entanglement group. What about the page curve? So we saw that Matchgate that we have page curve. Let's add some non-Gaussianity. What you will find is that upon introducing non-Gaussianity, basically the entanglement page curve, it flows monotonically to the universal one, so to the this one, and the convergence is smooth basically, and the deviation is plotted basically how much this curve, the color curve deviates from the page curve black one, and basically what you find is that there is an exponential decay with the number of non-Gaussian gates. Okay, so basically the page curve approaches the universal page curve with deviation that decays exponentially the number of non-Gaussian gates in turn. So overall is saying again that expansion of non-Gaussian gates is enough to recover generic behavior from the page point of view.
If not the entire to the averaging the possible partition of the type, then many want to partition by one.
No, okay, here we take 5%.
And to give matter or no.
I think yes.
Because I managed to average by three months of this. It could be that like the more entanglement part that for the smallest part, I mean it's not the same. It's because you need the time to yeah, because near to network.
Yes,
It's not going to
yes. No, I think I want to change it.
But if I consider the navigate, we just take the first one and the next one. They don't teach over.
Yes, but the idea is to get with the page view and waiting enough to listen to
Okay.
if you choose that the time saturation. And at that point, I think I use it.
Yep.
So this branch started from different timing. You don't take a state from the Gaussian and like
Well, okay, you can go for to get into the black UniPa. This UniPa, you can do so for getting the house UniPa. But to get something in UniPa, well, it's not defined what is it. You have to define what is the document state. The way, more simple way of doing so is take that state being the output state of this like the define. So it's interesting. Maybe this another. This one?
And then Gaussian gates, which are also
Yes, this one.
so because like it seems get so it seems like that you're producing a lot of different games, right? So yeah, things we would see. So probably would you think that the way to each other soon?
I think no, because in this regard, the key for scaling is exactly the general scaling. Basically, the page cube for link for data is almost the same of for generic state, so you don't gain anything starting. Okay. Finally, some thoughts about the setup where you have alter measurement in the system, but basically recap generic systems have this volume load phase, so a small amount of measurement doesn't destroy the volume load phase entanglement, but match gates instead are match gate dynamic instead is the weak. So just a little bit of measurement destroy the volume low and get the log low. So how to remove the volume low? So the step is the gate. So you have measurement and you have some non-Gaussian gate. This beta now is basically telling you how much basically the amount of non-Gaussian gates you have per layer. With zero, basically you have an expensive amount of non-Gaussian gates per each layer, while theta equal to 1 means an intensity number of gates, intensity to the n. And in the theta between the 1 is the sub-extended. So what we found out is basically that this curve is basically the entanglement you get at the end as a function of log n, and here basically the different colors are different measurement rates, and without any Gaussianity, so without any non-Gaussianity, basically what you get is a log low. So because you lack non-Gaussianity, so you are like reproducing the behavior of generic Matchgate, so you have a log low. So these are straight lines. The entanglement is proportional to again. If you add instead non-Gaussian doping, basically what you observe is some super logarithmic phase where you have entanglement that grows faster than log n, basically, and then some area low phase. So basically you have that for small measurement rate, entanglement is like basically n to the output. So, but again, we wanted to recover volume low phase. One has to be n, proportional to n, as we have the generic system. So how to do so? Basically, we found out that the only way of getting field is theta equal to 0. And is injecting an extensive amount of instruction gates per unit of time. Okay? Theta controls how many non-Gaussian gates we have per each layer, so per unit of time. So what we found out is basically that to have a genuine volume load, which is one, you need that at each time step, you need an extensive amount of instruction. Okay, so it's not enough n non-Gaussian gate in total, you need n per unit of time. We'll now move to conclusions. So we studied basically three features, like of many body dynamics, and we saw difference between Matchgate dynamics and generic dynamics. With respect to entanglement, three features are basically unitary dynamics, ensure and monetary dynamics. So unitary dynamics, we saw that to take a Matchgate dynamics, but you have an extensive amount of gate, then you recover the universal behavior, so an entanglement growth that is linear in time. Second point, the page curve, Matchgate circuit state have a much lower page curve with respect to state. Just take n non-Gaussian gate, add them, and you will get the usual page curve. Third point is about monitoring system. So Matchgate system are very weak regard to measurement. So a little bit of measurement destroy the entanglement rate. But if you add enough non-Gaussian gates per bit of time, you can recover the basically stable volume of phase. This amount is precisely having an extensive amount of Gaussian gates per unit of time. So thank you.
Okay.
Yeah.
Take it. Okay, and there are a couple of questions really.
Okay. Questions again from the past. Can you find the relation development between the other effect statement? The predictable.
Well, analytically, or
I assume not an
so analytically, this setup measurement is very difficult to do. In fact, we tried something, but okay. So the release of numerically, so in fact, we can show you what I would say. You want alpha gain 1, volume loading proportion to n to the 1. So here is saying that to get alpha gain